with our kinematic relationships between position, velocity, and acceleration, we can analyze a lot of different situations. And sometimes you'll end up with special cases that come up frequently enough where rather than starting from the very beginning, it's worth analyzing them in a general way so that when you see them again, you can use those same tools and don't have to start over from our base understanding. And this is one of those. It's our idea of motion with constant acceleration. So what we can do is we can start with our relationships in some initial positions. Let's say initial position x naught, initial velocity v naught, initial time t naught. We'll set that time naught to 0. And do some analysis to come up with some relationships that, and then as long as we can say that we have constant acceleration, we'll just be able to use in the future and not have to rederive. So first, our delta t now just becomes whatever my time is. We're assuming we're starting at time 0 and my final time is just time. My displacement is now final position minus initial position. And my change in velocity is final velocity v minus initial velocity v naught. So if we have constant acceleration, our acceleration instantaneously is the same as our acceleration on average. It doesn't change, so they're equal. So we have a bar is just equal to a. We also know using this that my average velocity has to be just the average between my initial and final velocity, because if we look at this on a plot, for average acceleration equaling constant acceleration, like this is just a constant acceleration, that means that my slope is a constant. So the average value on any time interval is just going to be halfway in between my initial and my final. Again, this is true for constant acceleration, where this is a straight line dependency here. So this is velocity versus time. Average value will just be halfway in between, or v naught plus v over 2. We can also look at average velocity and say, okay, this is always true. Average velocity is equal to change in position over time. And now we can write using my new variables defined here that now my final position is equal to initial position plus v bar times time. So this is always true. But now we can take and combine that with our understanding of what my average velocity here is, which is true for only constant acceleration, and substitute that in for what v bar is, and say that, all right, this in terms of v naught and final v, I now have a way of finding that v bar. We can use a similar relationship for acceleration and say that my average acceleration is just equal to my acceleration at any point in time, which is the change in velocity over time, and find velocity in terms of v naught, a, and t. So my final velocity is equal to my initial velocity plus at. We can combine these further and say, hey, look, this top one, I can plug in my final velocity into this so that I don't have to like evaluate these separately and combine them later. So plugging that in, we get this relationship here, which can be simplified a little bit by combining the v naughts, expanding these terms, and you get my final position is initial position plus initial velocity times time plus 1/2 the acceleration times time squared. You can do some similar algebra, I'm not going to do it here, to get another relationship that eliminates the time. So this one's useful if I want to know final position and I know the time I'm considering. This one is useful if I don't know the time, but I want to know, let's say, my final velocity. So I can start with knowing my initial velocity, my acceleration, and my final position, and this will give me my final velocity. And you can always rearrange these to solve for whatever thing that you want to solve for. So, for example, it's possible that you might know the final velocity and the final position, but I want to know what acceleration does that correspond to, assuming constant acceleration. So we can just solve this for constant acceleration by subtracting v naught squared to the other side, dividing by 2 delta x, or 2x minus x naught, and we get my acceleration in terms of the other things. So this slide has all of the equations you need for most constant acceleration problems. And in general, what you're going to do is you're going to look at the problem, see what things do I know, what am I trying to find, and choose one of these expressions, or I guess this is another one and this is another one of those 4 equations that makes your life the easiest, that lets you get to the things you're trying to find from the things you know in the most straightforward way.